All right. Now for the last event, which is a panel discussion. Oh, there. Okay. Which is almost, panel's almost complete, so Greg?
Hold on, I'm getting a spam call.
Okay, go ahead. Okay, good. So the panel will be moderated by Harry Levine, who's my colleague here in physics. He just joined. Harry was, I think, from every report I've heard, played a major role in setting up the lab, the neutral atom quantum computing lab in Harvard, in Misha's lab. And he also spent time at AWS working on superconducting qubits. So he has a very wide understanding of the subject, and I'll just turn the mic over to him.
Oh, actually, do I go with you?
Maybe.
Oh, good.
Pass it down.
John?
Or pass it on further.
Oh, okay.
Who is this going to?
You can hold it, and then once whoever answers.
But we have microphones.
You only us two.
Oh, but
okay.
the people who don't, yes, okay.
Okay.
Great.
So I want to begin. Thank you to all of our panelists for wonderful talks today. They were super interesting and exciting to see how fast the field is moving in different directions. So I wanted to start, from my point of view, the field is moving very fast and often in directions that I was not expecting. I'm curious, for many of you who've been in the field for a number of years, have there been major surprises, or what have you been surprised by in terms of developments from the last year that has shifted your perspective potentially on what's happening? This can go to anybody. All the questions can go to anybody.
I remember QEC 23 seeing the recordings of the neutral atoms moving around being very surprising. Those were really cool.
I have been surprised by the developments in using quantum computers for AI. I think that there's been a lot of proposals over a long time, but I think somehow people are getting very serious about that, and I think that that's something that I personally find very interesting.
As someone who knows very little about error correction, I've been very impressed by what we've seen in error correction lately, but on both the theory and experiment side. But yeah, I can't really comment further.
What are some examples specifically?
I think everything that Jalev has been working on is really impressive, in part because it's just some really cool animations of what the actual atoms are doing, but I think it's the most convincing demonstrations that we're doing something non-trivial with error correction.
I'm kind of curious, on the theory side, it seems like there's a lot of developments that sometimes are hard to predict how they move fast, and sometimes it's hard to know how much further will they continue moving. So with Craig, you were talking earlier about finding factors of 4 and speeding up certain modules. In error correction, there are new codes being developed that are more efficient or have better encoding rates. How do you, with the development of those kinds of things, how does one project where things are likely to go forward? And yeah.
And I make like semi-log plots and I draw straight lines on them. And then even though you're like, I can't see any way that it would possibly do that, somehow it does. So yeah, my most recent factoring paper, I have one of these plots and there's like an empty spot in the bottom right. I have no idea how you would get there. But I do think cryptographers should just assume that we will, just out of caution.
They kind of need to know that it's possible to get there.
Well, I can't make
there's the reasonable chance to get there.
Yeah, I can't make a reasonable argument, or I can't make a concrete argument that we'll get there, but I can draw the straight line on the plot.
Yeah.
Does the development shift your perspective on like what the most important problems are to solve? In the sense of, like, one example is LDPC codes have emerged and placed more emphasis on long-range connectivity. It's not 100% clear that that's needed, but can offer some advantage, and that clearly has impacted the field in certain ways in terms of IBM's roadmap. Is that the case? Like, John, maybe I'll ask you, for example, has your perspective on the most important technical challenges changed, or is it all scaling? What do you think about that?
Well, I can just comment about the LDPC code. Now, I haven't understood them and thought about them yet, but our theory team has. And when they've looked at the paper, they have a lot of questions about how effectively there will be. And the problem is it's just not. You can't say a code is better because you did some, let's say, asymptotic calculation or whatever. You have to look at it very carefully, like Craig is doing. But you also have to do things like, well, how easy it is to decode. And the surface code's a very simple kind of minimum weight matching, but you can barely do that with superconducting qubits. I mean, people still have to work hard. You have a more complex code, it's not at all clear that you can decode that. And it's really a question, in my mind, about system engineering. The physicists like to show, one or two things or whatever, but you have to make sure that all 10 or 20 or 100 metrics are okay at the same time. Now, it's good that people are advancing and they'll eventually solve that. What I like about the surface code is that it's been pretty exhaustively studied, and especially with the Google team, I know when I was there that was great, and that you kind of know how things work and the like, so at least you have one existence proof. And then as people are developing other things, and things can get better. But you have to, it's very easy to hype things, by not, fully covering all the pros and cons.
Does that place emphasis on where more attention should go, for example, in academia or industry? More efforts focused on answering some of these specific questions, whether it's LDPC codes or otherwise?
That's right, yeah. And it's really getting down to the nitty-gritty of what you have to do and get it to work. And I think, I asked Craig the question earlier, and I think because he dove into, exactly how things would work, he would understand it better and know how to improve it. And it's kind of this deeper analysis that, you really need to know if it's going to work. Kind of a full analysis. I hope I'm representing you, Craig, properly.
I don't mind the compliments. That's all right.
Craig, how can we propagate your ability to intuit about new ways to improve algorithms? How can we make more people that are skilled in that way?
Yeah.
Besides ZX calculus, I took that to heart this morning.
I don't know. Well, I've been working with people on the Google team, like Tanuj Qatar, and just working with them, I see them improving and kind of learning. So like standard mentorship type things seem to work like they've always worked historically. That's the best I know how to do.
But I would say on the hardware end, you have similar things. And if you try to improve qubit performance or coherence, there's a lot of what I would call mythology out there, where someone, writes a paper about, the best qubit they ever made, best qubit, best fab, best, moment in time, all these things, and you don't know the fundamental physics and reliability of it. And we have similar issues.
Hero devices.
It's called hero devices, but it's actually superhero devices, because there's 5 things that are being chosen very carefully. Now it's good to have the existence proof, but we kind of need more things. So our company has a saying: it's metrology and not mythology. To kind of make sure we all understand, we have to very carefully understand things, and get good principled ways to think about things. And that's what we're doing. I know the other things are very useful, but we're trying to really home in on that very carefully, because if we want to scale, we want to build a complex machine, we really have to understand all these details, right?
Is that a perspective that you think is different now than it was 5 years ago or 10 years ago? Like when you were in earlier days at Google, you were also laying out roadmaps. I might imagine you also were thinking we should be very systematic about
I'm
this.
going to say in 2005, 2010, this was very academic, and I think it did pretty good. And then as soon as you have the startups, I'm part of a startup, then it got kind of crazy because everyone, I'd say the stakes got high. And then it got a little bit harder. Now, it's not by everyone, and there's a lot of groups, I really trust their data, but there's a lot of pressure on people to publish great results. And that, we are really trying to resist that and get good results, and then bring investors on board who understand that. Otherwise, we'll be in trouble.
In terms of those big results that come through, there's a number of milestone experiments, I would say, that have happened over the many years. Some of those are the quantum supremacy result from 2019. Others I might think of are the types of experiments that, William, you talked about, or experiments following your proposal, Andrew, where it's a bit of a toy problem where you can cook it up very precisely, you can do it in the lab. Can you talk about what the role of those milestone experiments is in your mind? Like, what makes them important? What has helped them to be a learning vehicle for the community?
So I can talk about the quantum supremacy experiment because I know that. So when everyone read that paper, it was all about, oh my God, you did a powerful calculation or whatever. And I tried to put in the paper that this was a metrology experiment where we measured the system error rate, and that the system error rate made sense from the qubit error rate, which is amazing that, and you use classical statistics. And I think, I forget whose talk today beat at the beginning, saying that what's amazing about quantum, and even though quantum is analog and very complex, the errors are actually digital and basically classical statistics. This is amazing. This is amazing, and that's the case. And that experiment kind of showed that was correct. So that's the kind of thing that these experiments can also do to tell you about how these machines practically work. And I think it's important for people to do that. In my mind, that might be the more important long term, is to really test the machines in a careful way.
Yeah, a few years after the supremacy experiment, the simulation techniques had gotten good enough that they could actually verify the data points that we couldn't simulate at the time.
Yeah, exactly.
And if you could think of that as like, okay, now it's dead, or you can think of it as like they confirmed the data points, like they showed the hardware in fact was performing beyond where we could tell.
I can say a few words too. I mean, I think certainly to me, what I learned from the experiment was what it takes to, at least a little bit of what it takes to go from theory to actual resource estimates and seeing how well it will do in practice. I think it was the first time I dealt so much in constants ever as a theorist, which was really interesting. And there were some surprises. I mean, I think the state preparation, the fact that we can prepare a hard random state with like surprisingly few gates, that was really surprising to me. I don't have a good explanation for that. Having some sort of model for that is another really interesting theoretical question. And I don't know if you kind of touched on this, but if you wanted to talk about like what sorts of experiments I would like to see done next. I think there was some mention of this, maybe also in Dolev's talk, but there have been some really exciting developments in quantum learning algorithms for learning from physical quantum systems. And there's been a recent focus in developing algorithms that are efficient both in sample complexity and time complexity. And I think we have some examples that are certainly asymptotically, that they seem pretty reasonable. And I think there's a lot that can be learned to see if we can actually make those practical and demonstrate those on devices today.
I'll ask a follow-up, which is, in a way, these are kind of benchmarks. A lot of this is talking about running these complex, difficult things on your quantum computer and showing that it works and using it to say, here's how well my quantum computer works. I can compare it to another quantum computer. I'd like to think also that we can learn something or gain intuition by doing experiments in the lab, maybe like by actually trying to implement one of these protocols maybe theorists are also learning to understand them better. Do you think that's true? Can you think of some examples where that does hold for?
Sorry, say again?
The thought being that by trying to work it out in practice and actually have it be implemented, that you can actually build some intuition, and that it could then maybe feed into your next proposal of what would follow.
Yeah.
So I'm not a theorist, but to chime in on what you're saying, I think that every single time we do an experiment, like when we also worked together in the past, somehow every time you do it, reality comes and bonks you on the head. Even if it's something that could have been done in numerics, it never becomes real until you do it in the experiment. And every time you do it in the experiment, it's like you always learn something. I don't know, what is it like from a theorist's perspective?
I mean, there were like some constraints of the system that were sort of interesting to run up against as a theorist. So one that I didn't really talk about was that, you can do classically controlled gates on Quantinuum's device, where the classical controls are sort of decided on the fly. But I guess my understanding is that because you want to sort of fix the qubit routing in advance, you can only control these gates using toggles. So basically, you want to have a fixed architecture where you only turn the gates on or off. And one question we needed to answer was what's the simplest way that you can implement a Clifford subject to this restriction? And we found a pretty elegant solution. I didn't really talk about it, but it was on one of my slides. So sometimes it can raise theoretical questions that you wouldn't have really thought of. That probably if I just wrote a paper about that, theorists wouldn't really find it very interesting. But then okay, if I can say the reason I care about it is because these are the hardware limitations, then suddenly it becomes interesting.
Yeah, go ahead.
There's also the fact that, we're approaching the point now where quantum computers will be good enough that, maybe you have some algorithm that you think heuristically should perform well, but you can't prove it. And you can use the device to kind of test this. Famously with classical computers, there was the simplex algorithm for solving linear programming systems where, you can show that theoretically in the worst case, it should be very bad. But when you run it in practice, you see that it performs really well. So similar things could happen with quantum devices as well, where, maybe you think, oh, I have this really cool way to prepare a Gibbs state for some system, but I'm not sure if it will work. Well, you can just test to see if it will actually work or not.
I wonder if that fits into this topic of co-design, where what you're talking about, I think both Andrew, you and William are a little bit of, here are some constraints. They're not fundamentally imposed constraints by theory, but they are practical hardware constraints, and they serve to motivate some creativity. Are there some examples that you can think? I mean, I guess you proposed one specific example already. Yeah, I guess with neutral atom quantum computers, there certainly are examples of that. You have one tool that maybe is a bit different, and then transversal gates have started to play a more central role in how people think about error correction, which has then stimulated. Yeah. Are there other examples of co-design or constrained thinking imposed by the hardware that has motivated new ideas that you can think of?
When I think about it, I have with 4 or 5 high-level constraints I shared in my talk, but I don't know, it's probably about 100 more that I kind of think about and wonder about, and it's kind of hard to describe that other than you have a proposal and then you think, well, what are all the issues you have to deal about? And then, I'm working on the very basic, end of fabrication. And, you have to choose a direction to go in. Hopefully it's a good direction. And then you start making it, you see what happens, and then you have to pivot if you need. It's hard for me to talk about that. Maybe on the theory end or algorithm end, it's different.
I think a good example of theoretical work being driven by hardware constraints is the Honeycomb code from Microsoft, where they had to build, essentially it's like a surface code ultimately, but they had to build it out of two-body measurements. And before that work, the two-body measurement papers were substantially worse. Whereas that paper, it's a surface code. It does just as well as any other surface code.
But it's a honeycomb lattice
Yep.
with 3 connections.
Yeah. Yeah, we know how to do that with CNOTs too now.
Okay, yeah, that's interesting, yeah.
I mentioned it in my talk.
Yeah, you just talk. 3 connections is great. But the question is it, how susceptible is it to failure for dropouts?
Yeah, so this is
That's the key. That's the system optimization you have to think about.
Yeah. So it is true that it is more susceptible to dropout. However, I believe Matt McEwen and Oscar Higgett and someone else put out a paper about a month ago describing how to do dropout handling in this 3-coupler code. So we have actual simulated data on that.
Okay. It's probably harder, but maybe not hard. You know,
Yeah,
you have to get the data from the qubits to know.
That's right. You might require better yield, but not infinitely good yield.
Yeah, but that's kind of what we're working on. So maybe all things are available then. Yeah. Okay. Thank you.
I guess like from the theory side, there are also these that I guess Craig is very familiar with, these optimizations to Shor's algorithm for factoring that, you know, were maybe motivated by this idea that maybe we don't have enough qubits to like store everything in like the vanilla way of doing Shor's algorithm. And maybe there are other things we can do, like you just, for the function that you evaluate, you only need like the least significant bit or something like this, and then this seems to actually work. And this also inspired, I would say, this algorithm by Greg Kahanamoku-Meyer and others on this Jacobi factoring, so like factoring numbers of the form p squared times q much more efficiently quantumly than if you just used vanilla Shor's algorithm. So there have definitely been like a lot of interesting algorithmic and theoretical developments that were inspired by these like constraints.
Actually, a really excellent example of an issue that would have been solved if we had hardware now, but isn't, is Chevigard et al., who are the people who came up with this more space-efficient factoring algorithm last year. There's an assumption in there that a certain interference effect will play out correctly, which relies on like some complicated superposition of periodic signals. And it would require, you would think, like a conspiracy almost for it to fail, but they can't prove it, like I can't prove it, and they had trouble publishing the paper because of this. And my paper also has this assumption. And if we could just try it and see, like this would not even be an issue at all.
It's I guess, the same thing with Regev's algorithm as well for factoring.
That's a very interesting example because that also points to quantum computers as a scientific tool to answer questions that nobody knows the answer about, even in like a relatively near term. So maybe on that topic, like maybe half the people on the stage are academic and half in industry. So we're talking a lot about the collaboration between academia and industry and what that model can look like. Dan, you talked about a version of industry trying to build large-scale systems and academia being very exploratory and trying to uncover different directions. It should hopefully be a symbiotic relationship. What is the academic side benefit from, like, what do you think is the most exciting part of being in academia working on this topic?
Well, in terms of just going back to what things are really surprising to me about how quantum computing has developed, I guess I have to hand it to the folks here on the stage that have worked out, have been actually implementing error correction and not just seeing that that one is past a certain threshold, so one is starting to get some returns from it, but really, at the stage of running algorithms with logical qubits, that's a lot farther than I would have. I mean, I thought, we'd have like a long-lived quantum memory, but actually to be, running a multiple logical qubit code is pretty impressive to me. I think, one of the exciting directions I think will be when academics get their hands on this quantum hardware. And I had thought that part of it would be sort of getting, I guess, like white box access to these devices, learning how to operate these devices, not necessarily as quantum computers, which is their primary intended use, but really as these highly engineered, controlled quantum devices where all sorts of interesting interactions could be implemented and time sequences could be implemented. Still, I guess, running as analog or not necessarily error-corrected machines, but just as machines that are already so good that they start showing the kind of quantum simulation kind of experiment that otherwise I struggle really hard to kind of create physically in the lab. We can just sort of farm the experiment out to some white box platform that we program through the web or something like that. I think that would be pretty exciting. But I do think that academics have a lot to learn from these initial sort of quantum simulation experiments with logical qubits and this very different perspective on what does an error-corrected nature look like. I think that's a pretty big frontier area.
I want to open it up to questions from the audience, but maybe I'll ask one more question and then we'll go to audience questions. If you're willing, would you put a number of years now on time to commercially useful quantum computing?
Well, if you're part of the QBI program from DARPA, that's 2033. And you hype up your proposal to meet that deadline.
See.
And you can see that spilling out into common discussion. So it's not something we can scientifically debate. It's by fiat. The government is almost not forcing us, but almost forcing us to say that. And in some sense that's okay because it gets people to think hard about it. But I think a lot of us are going to be disappointed because it's pretty hard. Now, there's some systems that I look at that I think are much more likely than others to get there. And, I don't know the way they're thinking about it, but it's kind of, it's so much driven by hype. And this question, I think it's good, and it's good for us, but I kind of hate it too at the same time.
Fair, yeah, I hate
but
it
it's
too.
a good question, nevertheless.
I want to be able to quote you on it.
Yeah, okay. But and that's the problem. Now, our company is certainly trying to do that quickly. And our plan is by using semiconductor companies, we can learn how to scale up quickly. But I wish the government believed us a little bit more. But
anyone else want to chime in on this?
I think there's an open question about whether ever quantum computers will be commercially valuable.
Yeah.
Okay, so
ever?
Yeah, we know some algorithms where quantum computers will give us some value, but not all, right? So when it comes to factoring large integers, that's an interesting problem. But we'll move past that, and everybody will just change away from Shor's algorithm, and then you can toss your quantum computer. So we need really a lot more things that are going to be valuable. I would say they will be scientifically. I mean, I'm just a scientist, so I can, not pretend to value money. But that they'll be scientifically valuable. I definitely feel that's pretty strong. Like we're going to make this bet that within the next 6-ish or something years, we will be doing chemical accuracy calculations on at least moderately complicated, not the sort of Mickey Mouse molecules, but something that's moderately complicated. And that I think is going to be quite interesting. And then for me as a physicist, like seeing all sorts of novel quantum mechanical phenomena and interactive quantum matter, the phase transitions in quantum circuits. I mean, that's all just wonderful physics, and that is quite valuable.
So I don't know about commercial relevance, but I feel like it feels like the field is on a predictable trajectory right now in terms of or it feels more predictable in the sense of people are like working toward fault-tolerant computation, et cetera. And I think if there were to be some significant surprise, I feel like it would be some really like comically surprising application that was really not expected. That was just like, that's hilarious. That's possible, and it ends up being some really important thing. So I feel like there must be something. So
Okay, that wasn't a number of years, but yeah.
it's not a number of years, but it's the
fine.
yeah.
Yeah.
There must be something surprising.
Okay.
I mean, technically, there are people who pay for quantum computer time today and like years ago. So you could argue like -2,
Okay.
but if you want it to be like they're doing useful things instead of they're willing to
That
pay
that is what
for
I
it,
mean. Yeah.
I have no idea.
Okay.
Yeah, that's a hard problem.
Yeah.
I mean, and, you know, our team, theory team, looked at that carefully, and they have some
The question of
things
time horizon.
The time horizon and what they would want to do that was valuable and the like. And you can make some projections, and it's all very good, but it's a hard problem.
Right.
But we could ask more concretely, let's say this, million qubits. So like when are we operating at the fault-tolerant quantum computing and 1 million physical qubits to be able to implement what Craig was talking about today? So
I believe
I'd put like
it's
10-ish years on it. I think.
Yeah, that's right, and I think that's fine. And our particular thesis with our company, for superconducting qubits, what they're doing now is great, but it's a box canyon dead end. If you just look at what 100 qubits looks like, and you try scaling that up, that's going to be a problem. We're trying to fix that and not make it a dead end, but we have to get it to work. And if we can get it to work quickly, then I think we can use the semiconductor ecosystem to figure out how to put it together in a sophisticated way. But okay, we have our work cut out. But we're trying to do things so differently. It's just really hard. It's slow.
I'll also note that if you're a security researcher who's trying to be ready in time versus if you're an investor versus if you're a government, your sort of probability of it being ready by a given year threshold is very different. Like if you're a security researcher, like a 1 in 20 chance is probably unacceptable to you. Whereas if you're an investor, maybe that's not nearly high enough.
Yeah.
Okay, I want to leave some time for questions from the audience. So why don't we open it up to questions?
Someone.
Here, I can run. Should I run mics over?
You need here.
Or you could ask the question and we could repeat it. Or no, we could just make Harry run.
All
That's
right.
fine.
No, you need the microphone.
So I got one quick question because I think we were talking about fault tolerant for a very long time, and since the last year we kind of start believing error correction works, as Craig mentioned. And I was just wondering, but it works not in a really perfect way. It's like we don't have a logic qubit with really, really high accuracy. And I was just wondering, is there any maybe experimental evidence actually can convince us that actually in the future we can reach the very low logical error? Like it's not going to be stopped somewhere. Like we can just have maybe 10 to the minus 3 level of error.
So in the Google paper on surface code computation below the threshold or memory, we did exploratory experiments with repetition codes, which we can get to much higher distances than surface codes. And in fact, I mean, in that experiment, we do see noise floors, which we believe are due to high energy events or cosmic rays, because when we put in mitigations for that, they get better. But those floors, if I remember correctly, are at like 10 to the minus 11. Roughly every few hours is when one of these events would occur. So I would say that is some concrete evidence that at the very least, if your computation is less than a few hours, it should definitely be possible to do it.
I think it's. I mean, it would. So, I mean, if like for example, taking the Google paper results, which are beautiful. I mean, the suppression is very clearly getting better. And then what we did, we went from distance 3 to distance 5 with like tens of atoms, but you can in principle do things with thousands of atoms. I mean, you should really expect that it's gonna, once the exponential has started, so before Harry, before his PhD, the gate fidelity with atoms was like 20 times above the threshold. Now everything is 2 times below the threshold. Probably will be at 5 times below the threshold in roughly a year. So I mean, you should expect that it's going to get low, right? I mean, it's really, we're at a very special time in the field where, you know, these things have been long predicted and you get to start to really see it. And yeah, no, I mean, I think across many systems you should expect, or at least across 3 systems, you should expect that probably within the next few years, people will start looking at long-lived qubits. And of course there'll be challenges, but I mean, that'll be just such an exciting thing to, yeah.
I think there's a few people who want to comment on this.
Can I just, you know, I think it's great people are measuring logical error rates and doing all those experiments. And it's great we're making logical error rates, but we have to make better physical qubits because a factor of 2 below the threshold is like building a transistor with gain of 2, which you can do something with, but it's really hard.
No, we want to bet that better.
Yeah.
How far below threshold do you want to be?
We have to focus also on making, you know, physical errors lower to, let's say, get it to gain a 10. Okay, and then it's easier to build the logical qubit. So for me, that's the thing more to focus on. But of course, the logical qubit rate is the figure of merit.
I guess I'm going to turn around and ask you, because everybody's saying, no, it's going to be good, it's going to be good, it's going to be good. I've heard that before. But like, what would be the thing that you would want to see that would finally, I mean, people talk about the qubit that lives forever or whatever. Is there like a time that you would call forever? Should the target be, I don't know, 10 seconds if you can find these? Well, I guess.
Yeah, so first of all, I actually am from math community. And the reason I'm worried about this is just I don't want to say I work on quantum algorithm for a few years, then suddenly someone tell me, okay, there's no quantum computer. That will be a disaster for me. But to answer the question, I think maybe 2 things I would really like to see is can people experimentally verify that we can have extremely low logical error rate and just demonstrate we can have a single very good logical qubit. And also, this is not just going to happen in it cannot just last for a short time. We need to have maybe a long time low logical error rate.
Thank you.
I mean, the current milestone goal for the Google team is to demonstrate a logical qubit that lives for, I guess, human perceivable amounts of time. And that will involve both improving the quality of the physical qubits and increasing the quantity. So I would say like the evidence that you're looking for is really being worked on. So we have preliminary things that indicate it should go well, and we want to sort of definitively demonstrate like, no, this is okay.
I'll make a snarky remark for fun, which our qubits already live for a human perceptible amount of time. Sorry, that was just the fun comment. But I mean, I think across all systems, I mean, it's like, they're in 2025. I mean, we are crossing characteristic thresholds. I mean, there's always possible that there will be some physics that prevents it, but that would be even more fun. You know, I mean, it's like the thresholds have been crossed. You know, you should really expect that it's going to happen.
Yeah, so let's see, starting with the 2019 experiment, you know, there's been a confirmation that noise is, you know, in these quantum circuits is essentially along the lines of what fault tolerance assumed, right? That it's independent and so on, roughly. So how worried should we be that when we scale up to very large numbers of qubits and really push the limits on various parameters, however it's done, that maybe these assumptions will stop holding and there'll be much more correlated errors. But, should we be worried about it? Should we be trying to mitigate, to have some plans to mitigate that? Or would you sort of say it's pretty clear we won't encounter that?
Well, it's kind of interesting question because it's hard to know about these correlated errors until you actually do a careful experiment. And like the repetition code, which is simpler, you saw the causal gray events, you know how to get rid of them. And, so then once you make the qubits good enough, you can test all that. I'm much more worried, about the fact that the qubits are good now, but it's going to be hard to yield a lot of them. And if you look, for example, at the IBM roadmap, they make a 20 qubit tile, and then they're going to scale up in the next few years, just putting together 120 qubit tiles. Okay, that's fine, and that's good now. But you're not going to make a million qubit. Are you going to make a million qubit quantum computer by scaling up 10,000 tiles? I guess it's possible. But I think you're going to have to make the qubits better and more reliable, and work on that engineering problem in order to really do that, at least for superconducting qubits. I'm sure other qubits have other problems too. That's our thesis for our company. Could be wrong, but that's the way we look at it. And let's just be very practical. You make your qubits on a wafer like this. If you're making 100 qubits, it's some fraction of the wafer. You want to scale that up to 2, 3, 4, 500, you're using more and more of the wafer. You can't pick and choose your spot on the wafer anymore. Your yield has to get better across the whole wafer to do that. That's a typical engineering and manufacturing problem. So, I'm going to say that physicists are generally not the best at manufacturing. Okay, we're trying to learn. However, maybe with the neutral atoms, you have manufacturing problems to make your trap, but they're going to be very different, and you may be able to get around these problems in a much clever way, and maybe that's why, in the end, they're going to be better. The limit might be manufacturing, not whatever strange qubit physics we think of as a physicist. And that's what's great about the field, is people are trying these things, and we're seeing what matters and what doesn't matter.
I'll mention, sort of related to this, I enjoyed watching Chris Pattison earlier grilling Dolev on whether their lasers ever get out of lock.
What's the answer?
What did you say?
What's the answer?
Well, it got a lot better once he left. No,
He said he'd never seen
well,
it.
that's actually true, but it's unrelated to you.
He said he'd never seen it.
He said what, sorry?
He said he'd never seen it.
Okay.
I will mention, in a sort of vacuous sense, we know there are noise floors like asteroid strikes, which we likely won't get to observe.
See.
Hopefully better.
Yeah.
Can we keep going for another minute or two? Okay.
Maybe to answer in a more serious way, I think the thing that's so beautiful about these atomic and ionic systems is that, I've done solid state experiments in my undergrad, and they're very challenging. There's always some confusing thing happening, and it's always very mysterious. Atomic and ionic systems, you can understand them very well, and like atomic clock people are obsessive. They really are very, very precise. And they are not ones to just there's just random blips in the laser and we're just going to be okay with that. People do very, very precise experiments, understanding the laser spectrum, understanding what the laser is doing, how the atoms are interacting with it, and things make sense and kind of check boxes. There aren't, extremely anomalous events. So I think that there's no reason to believe that once we start using these as quantum computers, it'll dramatically change.
And I also think that if you want to fabricate carefully, the people at, say, Applied Materials know equally well about materials that they know about that metrology. So, going to the experts to help us solve all our various problems is super important.
There's a question here.
So I wanted to ask experimentalists, should we trust this theoretical error model that the theorists are using anymore? Because now we can actually test this in the experiment and see if our simulated logical error rate is different from the physical error rate. Any thoughts?
Okay, I can.
It doesn't have to be an experimentalist, but
So I think at this point, at least with this is again a similar comment, is that with our atom system, we have a pretty good understanding of all the different errors and how they map onto the logical qubit performance. It's still not, perfect, but in terms of we understand how this exact scattering error exactly corresponds to XYZ, because there's a lot of levels in the atom. But if you characterize empirically, the bit flip errors, the phase flip errors, loss errors, et cetera, and then you use it in simulation, it agrees quite well in terms of like predicted performance below thresholds. So that's true in these systems. I think it's also quite true in a lot of the other systems as well. Sometimes maybe the error sources in superconducting qubits might be more mysterious, but at least they can still be very well characterized. And yeah.
I know at least in the Google papers that often they'll include an error budget and they'll have like a box called stray. And stray basically means like things that weren't in the model, or at least one version of the model. And I believe that box has been getting smaller over time. In fact, you could think of this actually as a design goal. So it's been told to me before by electrical engineers that they have this very simple model of like you have an impedance, a capacitance, and a resistivity. And this model is not true, but it often works. And people actually intentionally design circuits to follow that model to make them easier to work with. And in a certain sense, if you can't make your hardware act as if it had digitized PALIs, then you're in trouble. And yeah, you may make design decisions to enforce that the model is correct.
Also, I guess returning to the neutral atom part, I also feel like the place where the uncertainty about what the error is just somewhat lower, but I think it's still there. I think there's actually a lot of voodoo that's going to come out in the neutral atom business as we get deeper into things, as we demand ever higher fidelity. That certainly was the case with the ion trapping work. We love to report the fact that we're so far away from surfaces that we can ignore them, how lovely that is. But there's surfaces on all the optical devices that are generating all of the light that's going into our systems. And beams can fluctuate around, and somebody's thumbprint can go somewhere, and all of a sudden your quantum computer doesn't work. I mean, there's like a way in which optics is like extremely non-robust compared to like wires that are laid down on a chip. So there's still things that will be difficult, and also I think that as the field pushes further, we're going to find more of these like clear failures of the error model that we just maybe in hindsight we can figure out, but we didn't foresee.
Can we do one more question? Yeah, question from Errol. I'll bring you the mic. Thank you. Oh, sorry, you keep this. I will take this one.
I really like Dolev's comment that application could be something hilarious. And I also find AI kind of hilarious. I don't think we understand why these things work, but they work beautifully. So I was wondering if, I just wanted to share my crazy optimism that maybe we can make a quantum computer and then just test some crazy ideas that you can never prove. Like, you can't prove that ChatGPT gives you great answers. So, just have some great ideas. Just qualitatively working, and then see it actually working on quantum computers. What would you think about these kind of super optimistic perspectives?
Like maybe humor is quantum mechanical, inherently.
Humorous? Sorry?
Humor.
Oh, quantum mechanical. Oh, yeah. Cost analysis would break down, I guess. But
I guess I'd want to hear the concrete idea, but yeah, I imagine depending on the idea, there's a big difference in success of working or chance of working.
I mean, what about QAOA? Do you? I mean, that's what I would suggest. Yeah, I think that's maybe one of the best examples we have of this is something we would try if we had the hardware.
Okay. Oh yeah, go ahead.
I guess somebody has to ask this, but a lot of us here, PhD students and postdocs, and I guess we're either looking into entering academia or industry. Any comments, suggestions? Don't do this. What is wrong with you? Anything at all?
I guess I'll share an anecdote, which is I sort of became a researcher while in industry, and one of my coworkers, Balint Pato, also wanted to become a researcher, and he decided to go off to academia, and he's very happy. And I'm also very happy. So there's, I don't know if I have anything to warn against.
I mean, so for me, coming from experimental AMO physics, it seems like a pretty special time right now that you can take the academic path and being like being in a company, the flavor of research that you're conducting, or even the setting that you're doing, where you're doing your work is very similar to what you might be doing in academia. It's a pretty golden time. I was talking to people that work at Atom Computing, and they just say it's like being still in grad school in the sense that they're still like playing with fun stuff. It's just that they have a whole bunch of technicians around to help them do it better and to write really good manuals. So I think right now is a pretty sweet time where I think you can't go wrong. So go for it.
Well, I would say you can't go wrong as long as you can get funding. This is probably on everyone's minds, but no one really knows like if federal funding is going to continue to exist in the same ways it has. There's some evidence that maybe quantum computing will be somewhat protected, so who knows? But at the same time, I've been a professor for 2 months now, so I don't know how much I can talk about my experience. It's been good so far.
Okay. Okay, last question, and then we will end. Right here.
It's been said, I don't recall who, that like the frontier of physics or science generally is lies in the next digit of measurement precision, and I think that's where we were getting earlier when we spoke about this noise floor and measuring errors very precisely. So do you think that say before quantum computing gives us anything of scientific utility, it's possible that quantum technologies as a whole, just due to better measurements, can give us something scientifically interesting?
So I think the answer is yes, in the sense of, for example, you might improve the technology to go make a much better atomic clock, and then you don't know what types of physics will lie there, and I think that's very enticing. I think for me, though, the thing that I find very exciting is that quantum computers allow you to do precision measurement of many body systems, like of complex quantum mechanical systems. And all systems that have existed ever on Earth or possibly anywhere, they have some finite correlation length or they have some finite correlation time. And now you can exponentially increase, how far you can go without having errors. And if one is going to go look for new physics, I feel like that's the best place to go look, because we just don't know what might exist out there. So that to me is the thing that feels like such an exciting time.
I guess I'll share my crazy idea that I don't know if it'll ever actually work, but I hope one day people try it. I want people to collect light from 2 arms of an Einstein cross, which have a 1 week delay, store it in qubits for that week, and then see if they can get coherent interference between the 2 arms to get a clearer picture.
That sounds fantastic. Let's end on the Einstein cross. Let's thank our panelists.